Okay. So this is the notebook that I prepared you. This is just some background images. I will go through what we need to do and then give you time to do that. We will use for today of, let's say, non-standard libraries. The only thing non-standard that we will have is PyDICOM, which is a library to read DICOM images. Given for the rest today, we'll use SciPy, NumPy, Matplotlib, and that's it. So what I want you to do is to read the DICOM file and just take a look at the headers to see if you can recognize all the parameters that we discussed. And then play around with the visualization and also play a bit with noise and noise metrics and some very simple denoising, which is the filtering. Okay, so you can start. I will be helping you around, and we will, I don't know, like every couple of tasks we can see my solutions, which I will anyway upload in the next days, let's say. Okay, oops, sorry, at the screen. So the first task was just to familiarize with what these DICOM files contain. And you can see that it's pretty full of information. As I mentioned in the previous lecture, they really have many more details that you will need. It says, as an example here, that it was acquired using a computed radiology system. The series description contains information about which kind of exam it is. Now, series descriptions, this is just for general knowledge, but it's good to know, is a field manually by the technologist during acquisitions, or maybe presetted, so it can contain useful information, but often it's unstructured. And it might be wrong, as it can be manually modified patient per patient. It tells you the acquisition direction, the body part, the patient age and sex. Birth date has been removed when, because of course all these data that you will ever work with are anonymized, has been removed. And now also the demographics, especially the demographics, are manually filled, so they might be wrong. Even if nowadays most scanners have a link to the software that also handles patients incoming into the hospital and scheduling of the day. So generally they are more correct nowadays. And now I can find it here because it has been already pre-processed, but sometimes they also tell you the technical parameters of the acquisition, if for your study it might be relevant. We don't care for the pneumothorax, but now I'm working as an example on a project on image standardization for a modality that is very acquisition dependent, and extracting all the technical parameters from the DICOM headers is pretty useful. Now, here it tells you the pixel spacing, which is the size in millimeters of each pixels. The format, it tells you that it's using 8 bits, so it's between 0 and 255, and it's an 8-bit integer, and that's it. You can iterate it another way. And now, the more interesting part. So you've seen it's a 1024 times 1024 image, so relatively big. But as I said before, in X-rays we have a lot of resolution, so you need huge array sizes. And if we do an image show, we get this, which is really not that nice. So what we can do? Well, first, we want to visualize that bigger. And here I task you with playing around with that. And so here what I did was first make the image bigger. And then I said to myself, OK, let's just focus in this large area on a range of about 200 times 200 pixels. Is it still good for visualization, or does it start to become blurry or patchy or things like that? But we can see that it's pretty OK. I'm using the gray color map because it's the most standard in medical, in X-ray. But you can, just to see the effect of doing that, you can play around with all the color scale that are available in PyPlot, which, if you go to the documentation page, you can see that it's like 100, if I remember correctly, or so. And yes, that's it. Oh, well, you can use the Vmin and Vmax parameters, because otherwise IMShow just takes the minimum and the maximum in that range, which is a valid rendering option. These images are naturally contained between 0 and 255, and you can use the whole range, or you can manually enhance the contrast by selecting just a small range, like doing like this. You can see probably much better on your screen than on the beamer. But here, like by selecting this very small range, you can see the ribs going over the heart, I guess, which are, you cannot see them, at least not on our screens in this light, this bright environment, when using the full image range. And these indeed are controls that the physician has. They can change contrast with just a touch of the mouse when reviewing them. Actually, reading them is the technical term. Do you want to go to the next part already? Or? OK. Now, we have mentioned last week, the effect of noise. And let's try to see what happens if we add some random Gaussian, some what's called white noise, which is random, non-correlated, and it can be modeled, therefore, just as an addition of a Gaussian. For every pixel, we add a random value with a 0 mean. We can see whether this makes sense or not. A standard deviation, and we do that for each pixel. Now, if you look correctly at the first question, you can see that the input image was in integers. If you want to sum the results of NumPy random normals, you can see that this is a float. This is not really an issue here because we have an automatic casting, so that's not an issue. However, the thing you can notice, which is an important concept we introduced last week, is that if we add a noise of magnitude 10, which is quite a bit, you can't really perceive it that much. Now, on the beamer, you don't even realize it's that. Now, if we zoom in quite a lot, the exact same image, we can appreciate that the noise is actually quite high. let me do like this. You can't see the ribs that well anymore now. Now, what does this tell us? So one of the things that I mentioned before, that noise is a task-related concept. So if your question is, my question is, can I see large structures when, let's say, I zoom out the image? We can add a quite high level of pixel noise, but if I want to take a look at, if I want to make use of the full resolution, noise in some way is impacting my resolution. This is what I was mentioning before. Now, last things that I asked you was to compute the mean square error. And, well, you can import from Sheikit image a function that computes this metric, but you can also do just the sum. By the way, be sure to specify to use float, because maybe NumPy does the automatic casting, given that this is a float, but otherwise maybe the sum will not work correctly. And we use the standard deviation of 10 in the noise, and the MSE is 10. So everything is working as expected. Let's say this could have been expected. Okay, so we'll let you play with computing the metrics for Gaussian after Gaussian filtering, and yeah. Okay, so let me show you my solutions. And here I introduce some the single simplest denoising strategy, which is filtering, and it consists in basically suppressing all high frequencies, which of course contain both signal and noise. But if you have white Gaussian noise, it spans all frequencies, while most signal is contained at lower frequencies, so it can improve image quality. To do this filtering, we use Gaussian filtering, and specifically, we will use this Gaussian filter implemented in NDI. There's also one implemented in Sheikit image or whatever. And we can take a look at the parameters that it uses. Of course, you get in input the image array, and a parameter sigma, which means this, which controls the strength of the filter. Specifically, you can see the sigma of a Gaussian as the size of the object that will be preserved. If you have something which is much smaller than this sigma, it will not be seen anymore in the image, while if you have something much larger, it will remain basically untouched. Specifically, they don't know, the filters don't know anything about millimeters or units of measure, so it's in number of pixels. And so first thing we need to do is to convert from our millimeters to see which we know how to interpret to pixels. And probably you studied convolutions in other courses, like probably in convolutional neural networks. When you're doing a convolution, you need to think about what happened at the edges, where you're convolving with something which is not defined. So you can tell the program whether to pad the image on the non-feasible region with zeros, to replicate the image, to wrap around the opposite edge, or I guess these are all the options. There is, in NDI image, there is no possibility to just crop the output. There is with other functions. Okay, so what I did is just to take from the DICOM header my pixel size. In this case, it was 0.14 millimeters. I also imported the structural similarity index. I will come back to that later. We don't really need this. Now, what I did here was to pass a list of sigma values that I wanted to try. We have pixels. Our pixel size is 0.14 millimeters. So what this we can filter, we can try a very, very light filter of 0.1. A filter of 0.1 is, as we said, it keeps untouched the structures that are bigger than 0.1 millimeters, which is basically almost all of them given how small our pixel sizes. Then I tried some logarithmic sampling, 0.2, 0.4, 0.8, and 1.6 millimeter. Now there was a question, do filter which is the smallest value that makes sense. You cannot, we are starting with a sigma of 0.7 pixel. This is really the smallest we can do. And filtering with a sigma of 12 pixels, 12 means a sigma is, it goes on two sides. It's like a radius. So it's filtering a diameter. This means that we are filtering almost 2 millimeters. And it will delete almost all of the features that we have in the image. So just for the sake of visualization and completeness, I've tried filtering both my noisy image and then also the original image. And then I saved the mean square error, computed exactly like I did before, and my structural similarity index matrix. And so these are my plot of the mean square error and of the SSIM. We can see that my noisy image with some very light filter already improves from the 100 value that I had before. It keeps on staying low when I filter it, but the more that I filter it, the worse it becomes, so this, the MSE value drops. While for our original image, we can see that its mean square error worsened. For the structural similarity index, on the other side, we can see that a light filtering greatly improves the perceived image quality. And when we filter more than a certain amount, the two images basically become of the same quality. Now, concerning the structural similarity index matrix, let's go back to the documentation of the function. We can see that it takes two images. Of course, they need to be the same shape. And an important parameter is the data range, because if you remember, we saw that it computes the similarity over a certain intensity of the image. So our image is between 0 and 255, so we need to pass the parameter 255 as a parameter, because otherwise it will use maybe 1, and it will get completely different values, even if probably just rescaled. Now, I've seen that the filtering on 0.2 millimeters gives us the best structural similarity index, so I'm going to apply it and showing it. Now, this was our original image. Let me try to make this bigger. Okay, we can fit all the 4 of them. Now, this is our original image where we can see all of the features. This was our noise image. You can see that given that we are zooming in, the noise starts to be quite perceivable. And you can see here that if I smooth this, I can see all of the small features that I get here with the same level of contrast. We mentioned in the previous lectures that our brain likes edges a lot. So smoothing is impacting the edges, and this is not something that we like very much. And but we can still perceive most features. Keep in mind that I'm zooming in. Now, if I go to the original, I can see how I'm losing some details. Actually, maybe too many details, but I don't know. Well, the code seems correct. Now, when you have to do a smoothing, of course, there is some, you can try the structural similarity index or whatnot, but as we said, it's the metric is related to what your objective is. So which kind of features do you want to preserve? The definition of noise is related to the task. There is no image which is best in absolute terms. So what happens in practice is that you need to do, you have a task-specific optimization of what you want to do. Like if you are in fluoroscopy, and so you need to acquire any 10 images per second, and you want to minimize those, and you want just to see the general shape of things, you can go with pretty heavy smoothing. Do not zoom in at all and accept the loss of image quality. If you need to diagnose, like in the pneumothorax, where you need to see the thin line dividing the region from the other side, you cannot smooth, so you need to acquire an image with as little noise as possible. Here I had this bonus task, which is just a neat trick to show that if you subtract an image from its a smoothed image from the original image, what you get is basically an edge detection algorithm. Okay, so I still have 15 minutes if you want to go and try to play with the downsampling and the upsampling. I will show you my solution in 5 minutes or 10. And let me know if there are questions, as usual. Okay, so let me quickly go over the solutions of my solutions. So I told you that there are 2 functions to handle interpolation, and one is from a Shikit image is resides from the transform subpackage, and there are lots of parameters. An important one, especially compared to zoom in and image, is the anti-aliasing feature, which is used when downsampling to prevent aliasing. How many of you saw it in some courses? Okay, I didn't prepare a couple of examples to show that, but I can show you. Now, when downsampling, we don't care about this much, but when upsampling, interpolating, instead an useful interest is what kind of upsampling is done, what this is doing is a simple interpolation, so just estimating which values are present between some points. And you can do that with a linear fit, basically, or you can use higher order interpolations, which might look slightly better. Or you can use order 0, which means a piecewise constant. Now, let's see. First thing that I asked you to do was to downsample by a factor 4 the image. And so this is what happens if I do with the anti-aliasing features equal true. We can see it's pretty smoother. We have a slightly lower resolutions for what we can perceive on this screen. While if I put it to false, we can see sharper edges, but some small features have some kind of ringing artifacts which we don't really like. Now, if we do the same for I wanted to show you the effect of okay, I'm sorry for trying to modify that at the last minute. Well, sorry, this is suboptimal, but just to show you. Okay, this is what we get is if we upsample by a pretty high, by a factor 3, a very small area. Now let me change the kind of order. If we put order 0, we have basically, it's called in mathematics nearest neighbor. I hope it's self-explaining. It means that for each pixel, it gives the same value to the 3 nearest pixels. So of course, doesn't look very nice. If we take order 1, it's a linear interpolation. It looks better. If we take order 3, it's a polynomial sampling, a cubic interpolation, and it looks more continuous while keeping a bit of edges. This is not, again, of course, you cannot invent data that you don't have, of course. We won't touch it in this course, but there is in imaging the whole field of super resolution, which means inventing data that you don't have. And up to a point, you can do something, let's say. While, okay, so here, the takeaway message of this part is still that here we are upsampling an image by a factor 3 or even more, and the quality is not that bad, which means that we can still see these very small, these are LED cables for maybe an EKG or something like that on the top of the patient. We can still preserve really nice resolution. There are lots of information in even small images like this, which was originally a 100 times 100. Okay, so that's it for today. I need really to run away for this department meeting. Do we have any question? I will improve the comments on my code and I will upload it on the drive, and we'll see on Thursday.